Saxon's Calculus Lesson 79 is about properties of limits and then some special limits. So on pages 389 and 390, they remind you of what the properties of limits are, but they're not what you would not expect. So if you have a statement where you're doing f plus g, and then you've got your equations then that you're putting together, whatever the limits were for f and the limit was for g, if you add those together, just like it's doing here, you're going to get the correct answer. If you, number 2, need to subtract, then you're doing f minus g of x. You're going to subtract their limits to get their answer. Number 3, the limits of the products of two functions is the same as multiplying. So fg of x is the same as multiplying those limits together. Number 4, the limit of the product of a constant and a function equals the product of the constant times the limit. So if you've got a number that's in front of f of x, you are going to multiply that number times the limit of this and get that answer. Number 5, if the limit of the denominator is not equal to 0, and they have to clarify that because now you're talking about fractions. The limit of the quotient, the dividing of those, is the quotient of the limits. So exactly the same thing again with the f over g. And then number 6, if the value of a function g of x is greater than the value of another function f of x and less than the value of another one h of x, and if f of x and h of x both approach the same limit as x approaches c, then g of x also approaches the limit as x approaches the c. This property is called the pinching theorem or the sandwich theorem because the limit of g of x is pinched or sandwiched between the limits of the f and the h. So they write it with the greater than and less than symbols to try to show that to you, but I feel like as you work through them, it's a quick grasp of the concept. So in example 1, it says the limit x going to 2 for f of x equals 3 and the limit x going to 2 for g of x equals 9, find the limit for x heads to 2 for, and then it says 2 f of x's plus pi g of x. Oops, ran into the hole there, and then they closed that bracket. So we're going to take 2 times the answer for the f, which was 3. So basically 2 times 3 plus pi times g of x, which was 9. And then that works out to be 6 plus 9 pi when I write it in the proper order. And it really is that simple. Example 2. If the limit of x going to a for f of x gives you L, can we say that f of a exists? This problem is a typical problem that appears on standardized tests requiring calculus. In order to answer the questions, a complete understanding of the concept is required. Future problem sets will contain tricky questions like this one to enable students to develop the understanding that will allow these questions to be answered with confidence. To answer the question, we need to know that the limit of f of x as x approaches a, which is what it's saying there, is a statement about what happens at values of x close to a. It is not the same as plugging in f of a. So it's not the same as putting a into f's equation. It's talking about what happens to the x as it gets closer to the a. Okay, so then they conclude with, I think I lost where I was. approaches A, statement what happens X is close to A. Nothing to do with f of A. Which is the value of f when you plug in x equals A? Thus, the fact that the limit exists, so this statement said it existed, does not imply that f of A exists. So don't get tricked with the fact of if I plug A in here and then I approach the same A, yes, I will get the L. That's not what it's saying. So basically, no. Now, example 3. Is the following statement true and why? So they give us the limit of x going to 3, f of x equals L, then f of 3 equals L. Now we just did something similar in which we said, no, you can't make that statement, and this feels like exactly the same. So is the statement true? No, it's false. Same reasoning as we just talked about. And then it's asking for the y. So for their y, they decided to do a graph to show you. So if you have a function graphing some sort of a curve, and when you get to the 3, you could end up with a dot here, which would force a gap in the function. That's why it's false. I can be approaching the 3 from both sides and getting a different answer than where I necessarily fall on the curve. Example 4. If f is a function such that negative x squared is less than or equal to f of x, this is that pinching question, which is less than or equal to x squared. I want to make sure I didn't make it write something wrong. If f is a function such that less than or equal to the f of x, less than or equal to x squared, okay? For all values of x, evaluate the limit x approaching 0 for the f of x. Okay, so basically, if I plug the 0 in to this statement, I am saying that this f of x function has to be between, and if I plug in 0, negative 0 is still 0. And if I plug in 0 here, it squares to 0. So if these are the same, by definition, this is pinched to be the same as those two zeros. So f of x has to approach 0. 0 would be the answer there. And then part B are special limits. Okay, so here they are. The limit of x going to 0 for 1 over x, that's undefined. Why? Because I can't get a 0 in a denominator. The limit of, and again, I would have these in my notes, the limit of x yielding 0 for 1 over x squared is infinity. Now, if you think about that, you're approaching 0, and it doesn't matter whether it's positive or negative, it's going forever in those directions. And then the other thing that they did was they showed you the graph to prove this to you. If this 0 is creating an asymptote here for the y-axis, then when I graph it, my two curves are hitting on either side of it, and therefore I can't touch it. On this one, because it's 1 over x squared, we know that it graphs a curve, and because it's positive, it's swooping up. So that might be helpful in understanding that it's climbing forever. That's why it's infinity. So then the limit of x approaching 0 for negative 1 over x squared will be negative infinity. And the picture there to help is that this is now falling because the negative out here changed it, and so it's negative 4 forever. Okay, so now that you know those specialty ones, Oops, just a second. At the bottom of 391, they tell you most of the functions in this book are well-behaved functions. If we need a function whose behavior is somewhat aberrant or does not fit the norm, we usually design a piecewise function that has the desired behavior, but this is not always necessary. So two following functions are famous for not having limits as x approaches 0. And they are y equals the absolute value of x over x. So no matter what positive or negative, positive comes out and it's divided by the same thing. And y equals sine of 1 over x. All right, so they chose to graph those to show you why that works. And I kind of just verbally gave that one to you, but not really its graph. So if you are plugging in 0, you can't get 0 in that denominator. But if you plug in 1 or negative 1, with 1 you get 1. With negative 1, you get negative 1. And then each of these little decimals in here are basically the same. So I'm going to put an open circle here and an open circle here because it's going these directions. That's what that graph looks like. And then for the sine of x, of course, you know that that's the curve. What's different in this one is that there is a gap where you don't have any of your curves, however that might have been, they don't exist in between here. There's that gap because it is fractional. So that's why they do not have limits that exist.